Right, well, good afternoon and welcome to the session on building JavaFX interfaces for the real world. Well, almost real world. My name is Simon Ritter. This is Angelo Caicedo, my colleague. We are technology evangelists at Oracle, and we have spent a lot of time working on today's presentation. Every year that I come to Java 1, I promise myself that this year is going to be different. And this year, I'm going to get everything ready by the time I leave for Java 1. So the demo that we're going to show you at the end, I finally got it working at 6 o'clock this morning. So next year, I'm going to get everything working by the end of the presentation. Next year, I'm going to get everything working before the presentation. Right, so I worked for Sun for 14 years before we were acquired by Oracle. And one of the things that you notice when you start working for Oracle is that lawyers get involved. And so every one of our presentations now has to have a safe harbor statement at the beginning or at the end. And as you can see, it says, the following is intended to outline our general product direction. Well, I can pretty safely say that this is not our product direction. Bear with me and you'll see what I mean. So what we're going to talk about is how you can interact with machines. And so we'll talk about the concepts of the man-machine interface, how things have changed over time, how things have progressed in terms of how we actually interact with these things called computers. Then we're going to go into some of the technical details of how you can use Java to work with different ways of interacting with computers. So we're going to talk about two big things. We're going to talk about Java and the Kinect sensor. So I've got that taped to the chair there. And I'm going to talk about Java and reading your mind, kind of. So that's like I say, it's not our general product direction. Yeah, despite what some people might say. And then the last bit, we're going to talk about JavaFX and how you can interact how you can get user interfaces to interact with gestures detected by the Kinect. And we've got a really nice demo based on a casino, and we'll see how that works at the end. So let's start with the ideas of the man-machine interface. Now, it's interesting because this is really where it all started, certainly in my opinion, is that we started having the ability to use some kind of mechanical device for interacting with machines and producing output. So a typewriter is a good example of how we really started. And this really goes way back to the sort of 1870s when the QWERTY layout, Q-W-E-R-T-Y layout was first designed. And there's some misconceptions about why it was designed the way that it was. The reason that it is laid out in the form that it is so that you don't have commonly paired letters in such an arrangement that the hammers of the typewriter would be next to each other. So what you don't want is S and H or T and H having the levers or hammers next to each other, because if you type very quickly, when you type them together, they can get jammed. So the QWERTY layout is actually designed to spread the letters out in terms of their usage. Some people think that it's actually designed to slow down typists, but that's not the case. It's actually designed so that you can type very, very quickly without getting the keys to actually bump into each other.
Now that's not the reason. It's so that when they demo typewriters...
No. Actually, okay, I'm going to correct you on that one. It's the original layout before, who was it? I can't remember the company that took over. The original layout had the period, or the full stop, where the R is. So the original layout was QWE dot TYUIOP. And then the company that bought the rights to it changed it so the R was on the top row so that you could type typewriter only using the top row of the letters on the typewriter. So anyway, let's move on from that because that's a real digression into history. So if we go on, progress was clearly made. So now we have these lovely plastic keyboards that have a lot more keys on them. For a start. So you have the traditional QWERTY layout, but now you have a numeric keypad, you have function keys, you have an escape key. What you want to escape from, I'm not sure, but just don't go there. And so, you know, we have the same style of thing Obviously, we don't care about the layout being organized because from a point of view of bumping hammers into each other, it doesn't make any difference. But we're using the same layout that we've had since the 1870s. And then some very clever people at Xerox PARC came along, and they started designing this thing. This is really the very first mouse that was created. And it's the idea that you can have something that you can put on a table, a two-dimensional surface, and you can move the mouse around using your hand. So it's a very intuitive kind of way of working with something, because we like to move our hands around, and if you think about it, as I'm talking, I'm pointing at things and waving my hands around. So it's a very intuitive way of communicating with a machine, is to use something that you can position. With having a flat screen as well, you've got a two-dimensional surface that you want to work with, so it's very easy to have a mouse that allows you to move a pointer around on the screen, and then you've got the red button which you can press to indicate that's where you want to do something. So that was the first one. I rather like that because it was made of wood. So, computer science and woodwork, I think they go very well together. So clearly we've progressed from there, and we now have, very ergonomically shaped mice. We have mice that don't need a cable. We have mice that have lots of buttons and several scroll wheels and all sorts of things like that. But essentially the same kind of concept, a two-dimensional way of interacting with the machine on a flat surface. What we've seen, certainly more recently, is that multi-touch type of interactions have become a lot more popular. So this is an example of the Microsoft Surface, the first Surface rather than the one that they've just announced. And so what this does is it's the idea that you can have a table where you can interact with it, and you can have multiple points of interaction. So you don't have a mouse. It's still a flat surface, but rather than having a mouse, you can actually touch the table, and the table will know where you've touched the surface. And similarly, you can have more than one point where you can touch it, so you can do the traditional things of spinning things around and stretching and things like that. Great fun, those, because they can also have things that recognize shapes, and they can have things so you can put like a glass there, and you can add information around it and things like that. I actually built one of these for Java 1 a few years ago. I don't know if anybody came to that session. That was a great example of computer science and woodwork working closely together. Clearly as well, things like the iPad have become very, very popular. They have a keyboard, but it's a touch keyboard rather than a physical keyboard. And you tend to interact with it through much more sort of multi-touch kind of gestures and things like that. So this has certainly been a big swing in terms of direction for devices like this. The other big thing that's really driven interactions with computers is the whole idea of gaming, because gaming is a very different kind of interaction, and you don't necessarily want to have a two-dimensional mouse type of interaction. Yes, you can do that, but if you're trying to drive a car, you don't want to drive a car with a mouse. So you need something that's more realistic in terms of how you interact with things like a car or a first-person shooter game or something like that. And so we've seen the development of very sophisticated interfaces. Here we have the Atari joystick. I had one of these when I was a child. And it's great because now you've got a different way of interacting. It's still two-dimensional because you're still actually moving X and Y, but rather than moving the device, you're actually moving your hand, and you've still got the button so you can do some interaction in that way. Then people like Nintendo came along and they decided you actually needed more buttons, because that would give you more ability to do different things. So they had the idea of a sort of a thumb kind of joystick idea, and then various buttons that you could use with your fingers. And that's really sort of progressed. Now we have things like the dance pad, so that you can't only use your hands, you can also use your feet. So you can have one of these games where you play music, they show you where you're supposed to bounce around, and you can make a complete fool of yourself bouncing up and down in front of a computer. Clearly, it's different ways of interacting with the system. And then, very 1970s Buck Rogers style of interaction. Again, Nintendo have always been at the forefront of design for interactions. And so they came up with the idea of a data glove, where you could put some controls on a glove and then you could kind of interact with it. It's not really a true, well, I suppose it does have some bend sensors in it, but it's, a next generation of design. And then, of course, we've got the very familiar gamepad kind of idea, which is this thing that, as somebody of a more mature age, you watch children playing with these things, and they have this phenomenal dexterity of their fingers and ability to sort of move all these different things at the same time and interact with the game. But really not intuitive. I mean, a gamepad is very non-intuitive in terms of how people interact with it. So now it's become about gestures. The recent changes are all about, how do we become more natural in terms of our interaction with systems? Again, looking at gaming, you've got the Nintendo Wii. This was a real game changer, pun intended, in terms of how people interacted with games. Rather than having this complex gamepad, suddenly you had the ability to be much more natural in terms of your interactions. If you wanted to bowl, why would you want to press a combination of buttons in order to indicate how you're bowling? No, what you want to be able to do is move your arm backwards and then move it forwards in the type of action that you would do if you were actually bowling. And that's what the Nintendo Wii allowed you to do. So using an accelerometer, using various bits and pieces, they could actually monitor the movement of the controller and then feed that into the game and give you a much more realistic way of interacting with the actual application. And that made it much easier for people like my mother, people like children to play with these things and learn how to use them. Clearly, Sony came along and they decided they needed something similar. They had a slightly different approach. Yes, they had accelerometers built into it. But the problem with just having an accelerometer is you can't get precise information about position. You can get the relative information in terms of how fast you're accelerating. But it's very, very complicated to take the data from an accelerometer, combine it with gyroscopic data, and have some idea of where the device actually is. So what they did was stick a light on the end of the controller so that they could track that with a camera. And then you can get position data in the X and Y plane, plus the acceleration data, and make, again, a more natural kind of interaction. And then along came Microsoft, and with the help of some other people, developed the Kinect, which was, again, a big shift because it meant you no longer needed any form of controller to actually hold. So it became very natural in terms of the interaction because you could just move your arms around, move your body around, and there was no actual controller involved that you actually had to hold. So we have made progress. So let's talk a bit about how we can go about tracking gestures using the Kinect and Java. So the first thing is to have a closer look at the Kinect itself. And what you've got here is quite a complex piece of hardware. And for the price, it's phenomenal to think of what it can actually do in terms of giving you data about where somebody is in front of the sensor. So you've got a number of different things here. You've got a tilting motorized base. Okay, well that's not fantastically exciting, but it is there, so you can move it. There's a 3-axis accelerometer. Now, that's a useful thing because it actually can tell you the tilt of the sensor. But typically, you're not going to be moving this thing a lot, so it doesn't give you an enormous amount in terms of extra information. It's also got some downward-facing microphones, so it can actually pick up sounds, and because you've got 4 microphones placed along it, you can actually get some directional information about the sound. We won't be going into that in the Java part of this, but those are available in terms of the hardware. Then, really, you've got these 3 different parts to the front of it, which is the thing that really does the hard work, or at least in terms of gathering information. You've got a standard sort of RGB webcam type of camera. So it can take an ordinary type of picture of visible light and see exactly what's in front of it. So that gives you a certain amount of information in terms of, okay, that's what we could see as a human being. But then to give you much more information, or give the system much more information, you've then got an infrared light source. And that basically projects an array of point data, or point dots, not point dots, dots, onto the field of view of the sensor. And what that then does is use the reflected infrared light from those points, gathers that up, analyzes the intensity of the reflected light in order to give you some idea about how far away the actual points are. And so this is the really clever part, because of course you're using infrared light so you can't see anything as a human, and so you can get 3-dimensional information from this, combine it with the vision of the RGB camera, and really get some very sensitive data in terms of the sensitivity in terms of the size and scale and so on, of what is in front of the camera and in front of the sensors. And then you can combine that with other information to really get details about what the user of the system is doing. So if we look at the typical sort of information, what you've got is an RGB image. Okay, so that's just what you're getting from the webcam, somebody standing in front of the sensor. Then what that does is it uses the information from the depth sensor combined with the information from the RGB image as well, and generates a depth image. And what it can then do is it can actually identify a user from that. So it's more than just a simple set of data points that represent depth. It also has some knowledge of the shape of a human body. So it expects a human body to have, 2 legs, 2 arms, a head, and be a reasonable sort of shape. I've not tried standing on my head in front of the Kinect sensor to see if it still recognizes me. Anybody tried that? No, okay. I'm not alone then. I would be interested to see whether it confused. I suppose you could just turn the sensor upside down.
Try it now.
It's taped to the chair, but we'll try that later. Okay, yeah, so it has certain knowledge about the physiology of a human being, and it uses that to determine where it thinks a human being is. So you get a depth sensor image, and then what that does is it says, okay, we know the general shape of a human body, and we've got some depth information. And then it starts to infer where the different joints of the body are. So it gives different colors to different parts of the body in terms of the arms, the head, the legs, and so on. And ultimately what you get from that is a set of points which represent the joints of your body. So you get the position of your hands, elbows, shoulders, head, knees, ankles, and so on. So you've got a complete set of skeletal data which shows where a human being is standing in front of the sensor. And that's 3-dimensional data. So you've got the X and Y and the Z axis coordinates for each of those joints. And as we'll see a little bit later on, it's really quite impressive how well it manages to track things. Because if you think about it, when you move your body around, you can obscure different parts of your body. So you move your arm in front of your chest. How do you know that that's where your hand is? So there's got to be quite a lot of complex processing going on in terms of matching up the position of the points that it's detecting with the joints that it's actually reporting. Now, in terms of how we can go about using that with Java, well, there is this wonderful library, the OpenNI library, which is all about natural interaction. So it's been designed for all different types of sensors. There's not many other sensors that are like the Kinect. There is one other that I know of. But it's really designed for working with these types of 3-dimensional sensor. And what they've done is create a C++ library that allows you to access all of the information that's coming from the Kinect. And so you've got all these different parts to it in terms of the nodes of the library. So you've got the device itself, so you can actually, if you wanted to, have more than one. You've got the idea of the depth generator, so you can see the depth data that's being generated by the sensor. You've got the user generator. When it recognizes a user in front of the device, then you can get information about that user. Because the Kinect can actually track up to 4 people simultaneously in front of the sensor, so you can get information about the different users that it's seeing. Image generator is the RGB camera image, so if you want to project that as part of your application, then you can. The infrared generator, again, you can get the information from that and include that as an image into your application. And then you've got things like the scene analyzer and gesture recognizer. And we'll come back and talk about this a bit later on in terms of how that works and what you can do with it. The other nice thing is that somebody has created a Java wrapper around this. So there's a lot of J&I code which actually allows you to access all of these C++ functions as Java methods and Java classes. The only downside is that it hasn't been fantastically well documented in terms of the Java APIs. And so it's a little bit tricky at times to figure out what you actually have to do. Yeah, you can kind of relate it back to the C++ documentation, but it does sometimes take a bit of working out what's actually going on. So here's some Java code in terms of what you can actually do with this. So essentially, what you have to do first of all is get a context for your Kinect sensor, and that's really the kind of key part that you need, and everything works off the context. So you need context. In this case, what I've done is use an XML file to define certain things about the sensor that I'm using. One of the key things you need in there is actually a license key for one of the libraries that you use underneath. It's kind of bizarre. I'm not quite sure why they've done this, because they have put a license key on this, but they give it away freely, and it's always the same license key. So I've never quite understood why they wanted to put a license key on there, but it's there, it's freely available, you can use it, you just have to make sure that it's set up correctly. Then from that you can get your depth generator, so you can get the information about the depth points that are being reported back. From that you can also get a user generator, so that when the system recognizes a user you can get events about the users that are being recognized. You can get information about the width and the height of the images that are being processed, so it's 640 by 480 is standard. And then from that you can also use the depth generator and the user generator to give you a skeleton. Skeleton in terms of the users that it's seeing. And that's the set of data that you get in terms of the positions of the individual points. And you've also got a skeleton capability, which is the capabilities of the skeleton, I guess. Not too sure about that one. Then, from that, obviously you want to be able to do something useful, and the easiest thing to do is to get information about the user that's standing in front of the system. So here what we're doing is simply saying, okay, I want to get the position of the user's joints reported back as a skeleton. We convert that, there's a conversion thing that you can convert real-world position data into a projective way of doing things, because of course you've got a projective sensor that you're using, and what the system can do is convert that into more usable points from a programming point of view. And then you can just write yourself a little method where you can say, okay, give me a particular joint position for a particular user and report that back as a three-dimensional point in space. And you can say, okay, I want the skeleton joint left shoulder, and that will give you where the left shoulder of that user is. And so there's not too much code that you need to write in order to get a fairly sophisticated amount of information from the sensor. So having got some information in terms of like the skeleton and seeing what the user is doing standing in front of the system, then you need to start thinking, well, okay, how can we make that more sophisticated and start recognizing gestures? And so if we think about the simple description of how we're going to process gestures, what you really want to do is to say, okay, for the sake of this description, we're going to use our hands only. Obviously, you could have gestures that involve more parts of the body, but simply, we do a lot of expression using our hands. So how do we track gestures that we make with our hands? Well, the easy thing to do is, of course, get the position of the joints which represent our hands. So we've got two three-dimensional points that we can get from our skeleton. Okay, that's pretty easy, pretty straightforward. And what we then need to do is track the position of the hands over time. Okay, so we're going to say, okay, a gesture is a swipe gesture. So we're moving from left to right over a period of time. That's an easy to understand gesture. So we want to track the position of our hand and see whether it's moving from left to right. Then what we need to do is say, okay, match the position, the movement of our hands, arms, head to predefined ones, so that we can say, okay, that's a swipe gesture, that's a circle gesture, push gesture, wave gesture, things like that. And then once we've recognized those things, we generate events which will actually say, okay, we just got a push event, or we got a swipe event, or whatever. So that's the easy, simple 4-line description of how we deal with gestures. Of course, it's a little bit more complicated than that. So tracking the position of the points is fairly easy, because you've got a sequence of points that are being generated by the Kinect sensor. The libraries allow you to say, okay, continually give me the position of my hand, and then you can record that in a list. So you can have a cyclic buffer continually recording the position of your hands, and so you can develop a track of where your hands are moving. Problem is, okay, you've got a selection of points now. What do you do next? So you're faced with complex mathematics. You're faced with the idea of, okay, do you do linear interpolation? So you say, okay, if we're doing a swipe gesture, we start here, we go to there. If we do linear interpolation between that, we can predict the points that we should have passed through and how close are the points that we've recorded to that particular movement. And if they're close enough, we say that's a swipe gesture. You can do more complex things. You can do quadratic interpolation. You can do Bezier curve interpolation if you want to look for like a circular movement or things like that. And then there's this wonderful thing called hidden Markov models, which is about learning, or getting the system to sort of learn what a particular gesture is. And so you build up a set of data, and you can use a hidden Markov model to compare what the user has done against a predefined set of data and give you a confidence level of whether they've just done the same thing. So you could say, okay, I've moved my arm across. Did it look like the time that I did it before? Did it look like the last 10 times? That type of thing. So this is obviously, complex stuff in terms of lots of mathematics. I started this a couple of weeks ago, and I thought, I don't have time for this. So the other thing we've got a problem with is saying, okay, how do we recognize when a gesture starts and when a gesture stops? Because, of course, you move your hands around all the time. Are we actually doing a gesture or making a gesture, or is this simply we just want to move our hand to a different place within the field of view of the sensor? So there's got to be some idea of how do we detect the start and the stop of a gesture. Fortunately, there is a solution to this problem. And the nice people at OpenNI have produced a nice set of libraries which actually will recognize gestures. So they've done all the hard work for you. And so you can simply say, okay, using a gesture recognizer within the libraries, you can look for certain events that are happening in terms of particular types of gestures. So you can look for a push gesture, which is a Z-axis movement. You can look for a swipe gesture, and that can be left, right, up, down. There's a wave gesture. There's also a circle gesture. So all of these things are preloaded into the libraries and very nicely available to you. So what you need to do is set up a whole bunch of listeners. There's a whole bunch of events that are generated. And one of the things I found straight away is that the type erasure that happens in Java generics can cause a bit of a, not problem, but it just causes things to be a little bit more complicated than you want them to be. Because everything in the OpenNI libraries uses this iObservable sort of type. And then they have a particular type parameter that's used with that to indicate what type of observable it is. So you get hand event args, you get ID event args, and so on. But the problem is, of course, if you want to have a class that listens for events of a different type, so you want the hand event arguments and also the ID event arguments, if you try and say, my listener implements iObservable of type hand event args and iObservable of type ID event args, type erasure suddenly says, well, we don't care about the different type parameters, so we'll just say you're implementing iObservable. But that can't be done because, of course, they're the same type. So you end up with, in my sort of opinion, you end up with a lot more classes than you actually really want, because you've got to do separate classes to deal with the different types of events. But that's just a minor aside. So let's have a demo. Yes, let's have a demo. Got to remember which demo we're doing now. Right. So what I'm going to run now is, okay, so this is now, as you can see, showing you the image of what's coming from the Kinect sensor. Now, one of the problems with this is I'm going to have to turn my back to you because, of course, the sensor's over there, and I need to stand in front of it. So if I go over here, you can see it's gone blue, which means it's recognized me as a user. If I come a little bit closer. Now, in order for this to do what I wanted to do, I have to adopt the pose, which indicates that I am in the calibration position. Hopefully, there we go, it's crashed. Okay, that wasn't quite what I was expecting to happen. And in all the times I've tested it, that didn't happen. So, yeah, okay, let's try that again. Because I think it's, right, yeah, there we go, let's try that. That normally cool. Come on. I don't normally have this much problem getting it to, there we go. Okay, good. Right. It might be because of the bright lights, but I don't know. So now what we're seeing is the skeleton. And I've just added some information so you can see the position of my hands and you can see the position of my head. And what I've also done is I've included at the bottom there, that's a plan view. So it shows the Z-axis. So if I move my hands, you'll see that that actually shows me moving my hands towards the sensor. In fact, I probably can move my legs around maybe. What was it there? And then the top left-hand corner, you'll see that there's a number there which is actually varying quite a lot. And that's the distance between my hands. So for a simple sort of example, what I've done is to indicate that I want to make a gesture is to bring my hands together so that it will indicate I want to start a gesture. So now I've started a gesture, and so you see a little purple blob in the corner. When I move my hands apart, okay, there we go, that then tracks the position of my hand. So if I move my hand like that, I've made a circle, and then I can do a swipe, and I can do a push. So you just about see there. Let's try that again. Yeah, so you can see that tracks the position of my hands. Okay, yeah, that's all right. So the idea there is to show that you can track the position of the body, and you can track the position of the hands, and then you can record the position of the hands as well. So that's all useful information, but then my problem was, okay, so what do you do with that next? So what we then do is we say, okay, let's use the OpenNI libraries to detect gestures. So I'm just going to run this program first. I'll explain this later, and then run this. How are we doing for time? Okay. So now what it's doing is it's now waiting for me to create a gesture to actually start things. So if I do that, there we go, you'll see that now it's tracking the position of my hands. Fortunately, I didn't have to do the funny pose, but as I move my hand around, and you'll see that it's putting a little arrow as I move the arrow around, as I move the cross around. And that's basically saying it's detected a gesture, which is a swipe gesture, left or right, and then I can do up and down, and same thing. And then if I do a gesture which is a push gesture, then I make a little circle up here, and it says, okay, you've got a push gesture there, got a swipe gesture, and we can actually see, there's a few points where it gets a little bit confused, but it's not bad. It actually works pretty well in terms of detecting the gestures that are involved in that. So that shows the difference between my sort of first attempt of like, okay, can we track the position of the hands, and then the idea of, okay, using the OpenNI libraries and getting much better sort of results from that. So that's sort of like the idea of, okay. So that was the idea of the demo there. So the next thing was to say, okay, how about if we go beyond the idea of simple gesture recognition? Why don't we start thinking about, well, thinking about things? So how can we monitor what we're thinking and feed this into some kind of application? So there is a company here in California, in fact, called Neuroski, or Neurosky. I think they're Neuroski, but what they do is they've created a sensor which can pick up information about your brain, in effect. The really clever technology here is that it's a dry sensor, because typically if you want to monitor your brain activity, you need to have a whole bunch of sensors on your head, and you need to have all this jelly that's conductive so that you can get the information from the actual electrical information from your brain. So what they've done is come up with a dry sensor, which means you don't have to smear jelly all over your head in order to read your brain. So they've come up with this, and what you effectively get is this headset, which looks a bit like one of these hands-free telephone headsets that you use with a phone, but is actually something which picks up the electroencephalography information, or EEG information, from your brain. Now, it doesn't pick up as much as if you went to the hospital and had your brain analysed, but it does give you a reasonable amount of information. From a programming point of view, it's actually really good, because they have a dongle which plugs into a USB port. And what that appears to be, from the point of view of the operating system, is simply a serial device. So all you need to do is talk bytes across a serial interface. It's fairly high speed, it's 115.2K. And then they've got a proprietary packet format which is published. So it's very easy to look at it and go, okay, this is how you get the information from that. And so you can send, you get status packets to say when the headset's been connected, when it's been disconnected. They report two specific values about your brain activity, which is your attention value and your meditation value. So it's basically how much you're focusing on something or how much you're relaxing on something, so two orthogonal values. And then they also report back specific EEG values, so there's like theta, beta, alpha, and gamma waves that they can actually give you values for. It's not altogether clear how much value those are from a sort of interaction point of view. And then there's a bunch of raw values, which I've never quite figured out what those raw values relate to. So from a point of view of Java and the MindWave, which is what they call it, it's really quite easy. So we have the RxTX or JavaCom library that you can get hold of. So you can talk to a serial device. You simply set it up as 115.2K, 891 parity, and so on. And then you simply read and write packets to the port. And so you can parse the data packets. I wrote a library for this demo, which basically did the interaction with the dongle, read the data packets, and then generated events based on what packet was coming in. So you could say, okay, you've got a meditation packet came for you, or an attention packet came for you, and then you can do something with that with your application. And then you register the listeners for whichever events you're interested in, which is good because the raw packets come at a fairly high rate, so you don't really want to be flooded by those. You can just ignore those if you want. So from the point of view of the code, so what I did was I said, okay, you've got a little test here which implements the MindReader status listener and the MindReader brain listener. I'm sure when I was at university, if somebody said I was writing a thing called a MindReader, I probably would have been quite skeptical. But so I have a class called MindReader, and then you just say, okay, MindReader opens TTY USB 0, and then reads, sets up a connection for that, and then says, okay, request disconnect. The reason I do that is because if you've been using the system before, you might have a connection left over, so you request a disconnect to make sure that it has disconnected first. And then you add a listener for the status packets as your class as well. So what then happens is when you get a status changed event happen, you say, if we've started, so we're waiting for the response from the disconnect packet, then we say, okay, once we've got a response, we auto-connect to whichever headset is available. And then when we get the connection completed, we say, okay, mind meld complete. So we're now connected. And then depending on which value comes back, we can have a listener which says, okay, your attention is this, or your meditation is that. So let's have a quick demo of that. So I get to put on my very geeky headgear. So there's two things you have to connect. One is you have to put something on your earlobe, and then you have to have this one that goes on your forehead. I have this thing about like coming to computer science conferences and wearing bizarre things on my head. Okay. So what I'll do now, and I must remember, where are we? Right, so I must remember to turn it on, because that always throws a spanner in the works if it doesn't do that. Right, so what that's going to do now, okay, attempting mind meld. Connection established. There we go. Good. Now, so what I've done is I've basically set it up so you've got, on the left-hand side, you've got the attention value. On the right-hand side, you've got the meditation value. And then the lines at the bottom are the different EEG values in terms of the alpha waves, beta waves, and so on. I really don't know what the graph at the bottom shows, other than that I appear to be alive. And then I will attempt to meditate. That's... Oh, no, no, my attention is now fixed. There we go. So,
you're levitating.
So there you go. So that's the idea. Now, one of the things I got from this, because I was thinking of introducing this into one of my applications, is that it really doesn't work because you don't have enough control over the levels to make it. See, I'm now in complete meditation as I'm talking to you. Right, I'm gonna stop that. Okay, so.
And you work with that guy all the time.
So as you can see, that gives you some idea of the sort of information that you can get from it. Right, let me go back to the current slide. Okay, so now I'm going to hand over to Angela, who's going to talk a bit about the demo side of what we're going to do for the rest of the cable.
Okay, so as you can see, Simon is kind of the crazy guy from the team, and I'm trying to be a little bit of the designer so we can build decent demos. So what I'm going to show you, what I'm going to walk through is, okay, we want to put together a demo that is actually a casino. So let's do nice graphics, nice interface. And if you think about it, we're looking into having unusual kind of interactions with the computer, like you can see with reading your mind. So we really want to have different and unique user interfaces. We don't want the typical window with menus, stuff like that. We want to make it really dynamic, really unusual, and pretty interfaces. So JavaFX really fit really well. You can think about a lot of things, animations, you can animate a lot of things, you can play with the transparency of the components. And one of the best things that I found is you can actually get rid of your window itself, so you can actually have borderless application, so it actually blends really nice with your background. For the purpose of this demo, we need a full screen, so that's why it's actually square, but you don't need to. So I remember one of the very first demos that I did with JavaFX was a swimming shark. So it's actually pretty nice because it was just the shark, doesn't have any background, and the shark was swimming on my screen. So it can kind of get bigger as it gets close to you, so you have the reflection. It's actually pretty amazing to have a shark passing by your screen, right? So it's a lot of things that you can think of. You can have different shapes. It will think about Twitter application. You have a little dude on your corner of your window and popping up some bubbles with the messages that are getting for you. So things like that, really nice application that blend really nice with your background. And how do you do it with JavaFX? So it's actually extremely easy. So normally in JavaFX, we have your scene. So you have to first set it, the fill-in to be null. So if there is anything, just don't show anything, right? So just make sure you set that. And then for the stage itself, that is kind of the window that you normally have by default, you can actually set it to transparent. So you say, okay, I don't want to show anything. That's how you actually have that screen without any border or anything, right? So something nice. Then, again, nice features. For example, you don't want to have a conventional menu. So the idea for the menu here was that everything is hidden, and if you get closer to the bottom, the menu will just show up, just you know, slide in, or also from the side. So just your menus will just get into your screen as you move closer to the border. So things like that are very, very easy to program with JavaFX. The demo has a lot of animations going on, so we're going to see that the dice are actually passing by those lines. So you don't want to miss what is underneath when you have the menu popping in. So a few things that I did, for example, was to have transparency. So the menu is going to be transparent enough to let me see what is behind, but it's actually providing me with some information. So semi-transparent bar, very easy to do. Animation, extremely easy to do. We're going to see how animations were one of the trickiest things to build for this demo. For example, when you're playing poker, there is a lot of animations going on. You're just hitting the players with the cards. There is a sequence that you want to finish, a sequence that you want to follow. All those sort of things are really, really easy to program using JavaFX. Want to be able to customize everything, so you either can use the CSS. For example, the bar is actually using CSS to get a nice style for that panel, so it's making it a nice gradient. Linear gradient is doing it nice. A little border. I don't know if you actually notice at the top of the bar there is kind of a white line that is giving you the idea, the impression of being a little bit pop out. So you can do things like that. Reflection, so you see that each icon has a reflection. Yeah, you can actually see it a little bit, especially with the coins at the really right-hand side. Zoom functionality, very easy to do. Push effect when you select one of the buttons, things like that. So you can really go into great level of details of how to customize your screen. For the menus, as I said, just an animation. We do have JavaFX provide you with two ways to create animations. One is through a timeline, and basically in the timeline, you have to specify what is going to happen over time. But because there are some animations that are very common, we also provide you with what we call transitions. So for example, if you're doing translate transition, translate is something that you do. Translate, zoom in, play with the opacity of the components. So those animations that are very common, we actually provide you already with the transition. So you don't have to create timeline and specify exactly what is going to happen. Very simple, you create the transition, in this case translate transition, and you're going to set from where you want to move to where. In this case, if I'm using the menu at the bottom, I'm just playing with the Y coordinates and from down up, right? Good thing is you can actually use the same animation for showing and hiding things. So one thing with the animation, you can actually play with the rate. So when you say play rate, set rate to 1, you just play normally, forward. You can set it to 2, 3, or 4, so you go faster, right? If you play with -1, you're going backwards. So it's the same animation that I'm using for showing and for hiding. I'm just going the opposite, the reverse. So actually very useful, a great way to reuse animations once they are created. Then again, the components you can play with opacity, transparency. It's really cool effects, really easy to do. As you can see, Simon and I are, you know, we like programming. I mean, we like creating demos. Maybe not very useful, but we love creating demos. One thing is the Scene Builder is a great tool to easily create user interfaces. I've never seen anything as easier. I mean, I don't think it can get any easier. So here, one sample, one point that I want to hit. For example, I have the image over there. You can even set the effect on Scene Builder. So forget about coding or going through the objects, anything like that. Through the Scene Builder, you can select the component, go to effects, and in this case, for example, you're creating a reflection. With the sliders, you can actually set what is the opacity of the top, at the bottom, what is the fraction, how much of the components you want to see reflected, and stuff like that. What Scene Builder is going to do is it's going to generate all the FXML file. There's just a file. And that file gets loaded into your applications. You normally have a FXML loader. It's just one line. You call the FXML loader, load this file that was generated, and there you have. Everything is actually generated for you, injected for you. So you're just injecting the components into your Java code. So it is fantastic. I really enjoy it. Again, so a lot of animations, a lot of things like that, also for styling. In this case, we do not have a lot of components that we need to style. Pretty much it were graphics and animations. But for the components that we do have, we actually using CSS for the style. So we have, for example, a master color, very useful because what we normally do is the styles that we define are going to be based on that default color. So meaning all the gradients and all what I'm going to do is take the black and either go lighter or darker. So you can have a different kind of shades, but all based on black. If I change black, for example, to red without changing anything else in the code, you will get the second bar that you see, the second image over here. So very powerful. Style your applications. And then we have dark panel. This is how I define the bar menu. It's just a linear gradient using some of the functions that you have on CSS for JavaFX, like derive. So what we're doing is I'm getting the black and I'm going lighter. So things like that. So you can actually really change the style of your applications. Okay. Now back to Simon.
Good idea. Right. So Angela did all the hard work in terms of building the actual application that we're going to show you. So she did all the JavaFX side of things. What I then had to do was take the work that I've been doing with the OpenNI libraries and the gesture recognition and the Kinect and say, okay, how do we link that together so that we can take gestures and integrate them with the JavaFX application? So effectively what I did was built like a small library on top of the OpenNI stuff to give the kind of information that I needed for the code that we were working with, and use the library code to handle the gestures and everything work from that. The way that I did it was to say, okay, if we're dealing with non-gestural hand movement, so if we're just moving our hand around in front of the Kinect, then we'll treat that as a mouse movement. So we still need to have the ability to move a mouse around and a pointer around. So that's quite easy in Java because there is the robot class. And that allows you to say, okay, I want to move the mouse pointer to this particular point, and you can simulate mouse clicks. It's all about testing user interfaces, but it's actually very useful if you've got something which is not a mouse and you want to simulate the idea of a mouse. So you simply use the robot class to say, move the pointer to a position X, Y, and that works quite nicely. And then it's like, okay, so how do we process the gestures that we're getting from the OpenNI libraries and turn that into something that's useful for the application that we've got. So the way that I worked it was I said, okay, if we do a push gesture, we'll treat that as a mouse click. So if I need to click on a particular part of the application, I can move my hand around, and then by doing a mouse click or a push gesture, I get the equivalent mouse click. And then for the different parts of the game, we'll use the, in this case, I'm just using the swipe gestures to indicate which particular part of the game I want to affect. So in terms of the events that you get from the swipe gesture, you get the direction, as we saw with the arrows. So you get left, right, up, down. And you can treat those differently depending on what you actually want to do with them. So that was all good. This was about Sunday we were at this point. So everything was good. So we had the library, the Kinect stuff, we had the JavaFX stuff, that was all good. So all we had to do was bring the two together. Piece of cake, huh? So it's never easy, is it? So we defined an interface. We did this a long time ago. When we first started talking about this, we said, right, we'll define an interface that we're going to use for the application. So Angela knew which messages I'd be sending to her to control the game, and I knew which methods I'd be calling based on the gestures in order to control the game. So that was easy. Then, obviously, Angela wrote the JavaFX code. I wrote the OpenNI gesture code. And then we just need to integrate the two together. It's easy, yes? Actually, no. This is where we run into a slight problem. Because what I found was that I'm running on a Mac. I'm actually running Windows 7 on my Mac. What I found was that when I had the OpenNI library running on its own, no problem. When I had JavaFX running on its own, no problem. When I put the two together, in order to have the OpenNI libraries not interfere with JavaFX because of the application thread in JavaFX, I needed a separate thread to run OpenNI. So fine. Java has new thread runnable. Great. So I create a new thread runnable with my code in it, and I start the application up. And the moment the OpenNI libraries go and try and get some information, boom, JVM crashes every single time. Some native code somewhere way down in the OpenNI libraries, I have to say, not the JVM, was doing some sort of memory access in combination with the JVM and the JavaFX libraries and the native code under there. Something was a weird combination that just crashed the system every time. So I'm then faced with the situation on Sunday with, okay, so how do I make this work? If I can't do it using, a thread and doing it that way. So I came up with a solution, which is there is always more than one way to skin a cat. And so basically I wrote two applications. One was what I called my gesture sender, and that is just a loop that sits there looking at the OpenNI libraries, looking for gestures, and then it sends it through TCP/IP over the loopback to a particular port. And I listen on the JavaFX code on a particular port, and so that way when I send a message, I pick it up on the other side, and the two address spaces remain nicely separated, and therefore I don't get a JVM crash. So let's move on to the final demo. I had to put the...
Is that a picture of you there?
That's me, yes, yes.
On the right?
Actually, before I go on, I do have to thank Andrew a lot. This is Andrew Davison, who has written a wonderful book about Kinect hacking and a lot of...
Where's the money?
And his book was very, very useful because he resolved a number of things in my mind in terms of the way that the code works. And like I say, the Java APIs are not well documented, and so if you want to buy his book, you will find there's an enormous amount of information there, which really does help in terms of using those APIs. So I really do have to say thank you very much to Andrew for that. Yes, I must admit, I went back and watched a little bit of Minority Report because it's always fun to watch that sort of classic bit of film of Tom Cruise there, not Simon, Tom Cruise doing the wonderful thing of that, the sort of wiping things around and stuff like that. So let's move on to the final demo. See if we can make this work. Right. So the first thing I have to do is I have to run the gesture generator. So this was the other program. This is the one that actually just basically sorts out the connection. So it says at the moment it's attempting to connect to the listener. And so I just did it that way around so that I didn't have to start them both up at the same time. I could start one and then the other. So it's just sitting there trying to connect to a port on the other application. So if I run the casino application now, hopefully, it's going to, oh, good, excellent. Right. So, again, I'm going to turn my back to you. So the first thing I have to do is, right, so I've got the mouse. I now have control of the mouse, as you can see. So if I move, okay, so the menu comes up, and then mouse click, there we go. And so we've got a fruit machine, and what I can do is I can use a gesture to indicate that I want to pull the lever of the slot machine. So if I do a swipe down, we get a fruit machine that runs, and so obviously all the JavaFX code is Angela's wonderful animations, and there we go, we won. And then in order to return to the previous screen, we go back to there, and then let's see if we have this side now. Okay, so let's go to the blackjack table. There we go. So bring up blackjack. Now, what I can do is I can say, okay, so I want to bet this player. So I'll do that, and then I want to bet this player. And then what I'm going to do is I'm going to start the game. So again, so these are all the animations that Angela did. Is that correct?
It might be, yeah. It looks like.
Okay, we might have a slight problem. Oh. Ah. Okay, I don't quite know why that happened, but I'll run that one more time, shall I?
The problem with gestures, you're really going to make something you didn't want to make.
Yeah, we did. We've been plagued by a null pointer exception. So let me just. Bear with me. Okay, right, let's just run that again. So just run casino. Okay. Right, so we go again. Okay, that's good. That's better than before. Okay, so now I think. Oh, no, that's not looking so good. Oh man, why does this always happen?
The demo guys have not been.
Yeah, they've not been good to me. Okay, so I'm afraid we're out of time. I can run it one more time if you want, but I think you get the idea of what I was going to do. The gesture, basically, I was going to use two gestures. One was to do a twist, which was just an arm down, one to do a stick, which was an arm up, and then the game would play. I don't quite know. There doesn't seem to be anything in there that's stopped working. But anyway, so thank you very much. I think we've got 2 minutes for questions, if anybody's got any questions. So